Hello friends, welcome to Abdemi's YouTube platform. Today we'll be considering a typical problem from thermodynamics. See what the statement of the problem is. At 27 degrees Celsius, 2 moles, be careful, 2 moles of an ideal monoatomic gas occupy a volume V. The gas expands adiabatically to a volume 2V. Calculate the final temperature of the gas, change in its internal energy, and the work done by the gas during the process. Given R equal to 8.31 mole joule per mole Kelvin. So we have a ideal monoatomic gas. Its volume is V1 and call it V at temperature 27 degrees Celsius. 27 degrees Celsius means 300 Kelvin. So at 300 Kelvin, 2 moles of gas are there. Now it is expanding adiabatically to volume twice of V. So final volume V2 is 2V. Temperature is not known, temperature is T Kelvin, let us assume, and obviously 2 moles remain as it is of gas. Now during this process, that means volume of the gas occupied at 300 degree Kelvin is V, and these 2 moles of gas expands adiabatically to volume 2V, and the final temperature is T Kelvin. We have to find the value of T first in the first step. So before we proceed, let us calculate what is the molar specific heat for a ideal monoatomic gas. Consider in moles of gas, which is monoatomic ideal gas. Now, if I increase the temperature of the gas by delta T, then what is the heat required for this particular gas? If the temperature is increased, keeping the volume constant, then Cv, if it is molar specific heat, of the gas, then the heat required to raise the temperature by delta T for this n moles of gas, monoatomic gas, is obviously NCV delta T. Alright, now we know dq equal to du plus pdv. pdv is nothing but dw, work done by the gas. This is actually dw, external work done by the gas. But since the gas maintains constant value, that means volume, that means the temperature of the gas is increased keeping the volume constant, so there is no external work done by the gas, since dv equal to change in volume is 0. Therefore dq is equal to du. But for n mole of such gas, what is the value of u? So since there are n moles of gas, so in that how many molecules are there, n multiplies by Na being Avogadro number, into number of degrees of freedom of monatomic gas is 3 into half kT. So at temperature T, the internal energy of the gas is equal to n into Na. N is the number of moles, Na is the Avogadro number. That means how many molecules are there per mole. So total number of molecules in n moles of gas is n into Na, 3 being the degree of freedom for a monoatomic gas, and half kT is the energy, kinetic energy of a single atom. So we know this half kT is the energy of a single atom at temperature T in a gas per degree of freedom. Energy per atom per degree of freedom. So there are 3 degrees of freedom and there are n into Na number of molecules. Energy per molecule per degree of freedom. Energy per molecule per degree of freedom. So half kT is the energy of a single molecule per degree of freedom. That multiplied by 3, 3 is the degrees of freedom of a monoatomic gas, molecules of a monoatomic gas, and there are n into Na number of molecules in the gas. So du is actually n Na k 3/2 delta T dt, you can say. Okay, so dt, you just consider that we are increasing the temperature by delta T amount. So I write this as delta T. Okay, this is delta T, change in temperature. So this du is equal to dq. So dq equal to du. So I can write n Cv delta T is equal to Na into k is R, 3/2 into delta T. So I get, they cancel each other, they cancel each other. So Cv is 3/2 R. Molar specific heat of the gas at constant volume is at constant volume. Cv is molar specific heat of the gas at constant volume, and that value is 3/2 R. Now Cp, which is molar specific heat of the gas at constant pressure, Cp minus Cv, we know it is R. So Cp is R plus Cv, and in this case Cv is 3/2 R, so it is 5/2 R. So Cp by Cv, which we call gamma, is actually 5/3. Okay, so this is okay. Just we are considering n moles of gas. We are raising the temperature of the gas by delta T amount, keeping the volume of the gas constant. So dq equal to du plus pdv. It is coming from first law of thermodynamics. So dq equal to du plus pdv. Now since the volume is remaining constant, so dv is 0, so dq equal to du. Alright, now this dq can be expressed as n Cv delta T, because we are considering n moles of gas, monoatomic gas, n multiplied by Cv multiplied by delta T. Now U, the internal energy of the gas, can be expressed as half kT. Half kT is the number of, it is the energy per molecule per degree of freedom. So half kT is the energy of the gas per molecule per degree of freedom multiplied by 3, because for 3 is the degrees of freedom of a monoatomic gas, multiplied by n into Na, the number of molecules of the gas in n moles. So du is equal to n into Na into k into 3 by 2 delta T. So these two quantities, this quantity and this quantity, both are equal. Therefore, n Cv delta T equal to n R 3 by 2 into delta T. So Cv equal to 3 by 2 R, and from which we could find Cp, which is 5 by 2 R, and Cp by Cv equal to 5 by 3. All right. Now, with this background, let us try to solve the problem. Okay. So for this particular problem, we have found Cp by Cv, which is gamma, equal to 5 by 3. So Cp by Cv, which is equal to gamma, is equal to 5 by 3. Now, this particular gas, which is ideal gas, let P1, the pressure of the gas at 300 Kelvin, and here the pressure be P2. So I can write P1 V1 equal to 2 moles of gas equal to 2 R into 300, PV equal to RT. nRT. Remember, PV equal to nRT is the ideal gas equation. So P1 V1 equal to 2RT, which is 600 R. So P1 V equal to 600 R. This is one equation. V is the volume of the gas at temperature 300 Kelvin. And similarly, P2 V2 equal to 2R into temperature is T. We do not know the temperature. And V2 is twice of V. So 2 P2 V equal to 2 RT, or P2 V is equal to RT. These two comes because there are 2 moles of gas. Okay. So P1 V by P2 V is equal to 600 R divided by RT. So P1 by P2 is equal to 600 by T. This is one expression. Another is, since the gas expands adiabatically to volume 2V from volume V, so I can write P1 V1 to the power gamma is equal to P2 V2 to the power gamma. This is for adiabatic expansion, you can write like this. Now, P1 by P2 is equal to V2 by V1 whole to the power gamma. But V2 is twice V and V1 is V, so it is 2 to the power gamma. All right. Okay. So P1 by P2 is 2 to the power gamma also. So if I connect these two equations, we can find 600 by T is equal to 2 to the power gamma. So gamma T is 600 by 2 to the power 5 by 3, and temperature will be in Kelvin obviously. So 600 by 2 to the power 5 by 3, it comes around 188.99. So T is 188.99 Kelvin. Alright, so this part is over. So what is the final temperature of the gas? That is T equal to 188.99 Kelvin. Now, next part. What is that? What is the change in its internal energy? That is to be found out. So let us see how it can be done. So internal energy of the gas U is equal to how much? U equal to, there are 2 moles of gas multiplied by Na. Na is Avogadro number. Okay? And earlier also I used Na. Na is Avogadro number into half kT multiplied by 3. Since it is a monatomic gas, degrees of freedom 3, half kT is energy per molecule of the gas, which is in this case it is a monatomic gas. Half kT is the energy per degree of freedom per molecule of the gas. There are 3 degrees of freedom, and in 2 moles of gas there are 2 into Na number of molecules. Incidentally, here it is a monatomic gas, so number of atoms is equal to number of molecules. So it is 3 by 2 RT. Na into K is R. K is the Boltzmann constant. This is K. K is the Boltzmann constant. N is the Avogadro number. So U is 3 by 2 R. So delta U, change in temperature, change in internal energy is actually 3 by 2 R delta T. Okay, multiplied by 2. There is a 2 over there because this 2 is there. No? So it is multiplied by 2. So 3 R delta T. Do not miss to keep this 2 over there. So it is 2 multiplied by 3 by 2 RT. So 3 R delta T. So delta U, change in internal energy is 3 into R value is given. R value is 8.31 joule per mole Kelvin. So it is 8.31 multiplied by delta T is actually T minus 300 Kelvin. So this quantity, if you calculate, it will come out as 2767.48, but there will be a negative sign because this quantity is negative. So that much joule. So though the volume is expanding, the change in internal energy, because temperature has decreased from 300 Kelvin to 188.99 Kelvin. So change in internal energy is a negative quantity, which is negative 2767.48 joule. Third part, the work done by the gas during the process. So work done, if you use this rule, dq equal to du plus pdv, law of thermodynamics. Now since the expansion is adiabatic, so dq is 0. There is no heat exchange between the gas and the surrounding, and therefore du is equal to negative pdv, or I can write work done is actually negative of du. So dw, work done by the gas, is equal to negative of this thing du. So it is negative of negative 2767.48 Joule. So it is 2767.48 joules. So dW is 2767.48 joule. So changing internal energy, that is this much, and work done by the gas, that is plus 2767.48. Okay, so this is the problem. I hope you have understood. This is a very typical problem of thermodynamics. Many concepts are involved in it. If you understand, I think you will be able to grasp many ideas of thermodynamics. So I hope you have understood. So if you have any doubt, please revert back to us. Thank you very much for your listening. Thank you.